So what I'd like to discuss with you is something called completing the square. Nope, just square. Sorry. All right. What's special about these polynomials? So let's consider this one, that one, and that one. So the question is, what's special about these? Well, when you factor these, for this one, for example, you get x plus 5 times x plus 5, which is x plus 5 squared. And then when you factor the second one, you end up getting x minus 3 times x minus 3, or x minus 3 squared. And this last one, x plus 1 times x plus 1, or x plus 1 squared. So these are examples of what are called perfect square trinomials. That's what these are. These are perfect square trinomials. And it's sort of interesting to look at them geometrically, which we'll do in a minute. So my goal today is to take these perfect square trinomials, make a connection between this, a process called completing the square, and then graphing parabolas. So we're going to connect all of those things together. So first things first, why are they called perfect square trinomials? Here's one reason. Let's look at the first one, x plus 5 times x plus 5. Okay, and you may have seen this before, but it turns out you could think of this as like an area problem. So let me show you what I mean. What we're going to do is we're going to consider all the separate terms. So I want you to imagine we had a rectangle or a square, one or the other. Okay, and let's just think about this distance for a minute. Let's call that distance x. And let's also call that distance x. Okay? So if we just look at the portion of the rectangle that is bounded by x and x, we end up with this thing. And we know that's a square, right? And we actually know the area of that square. We know it's going to be length times width, or x times x. So there's an area of x squared contained in this red box. Okay. What I'm going to do next is I'm going to give these things a name. There's the 5. There's the 5. Okay? And what we can think of is inside of this region up here, we could sort of break it into pieces. There's 5 units along here, and then it's x units across. So we can actually get the area of this whole thing. Okay? So each one of these is going to be at x, because I'm saying that this is 1, 2, 3, 4, 5. So you could think of this rectangle has a length of x and a height of 1. So this has area x. So does this one, this one, this one, and this one. We could do the same thing over here. 1, 2, 3, 4. These things should be equal width. My picture is not perfect. But notice, look, same thing. This height is x. The widths are all 1, so this is x, 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 x. And let's just start to think about what we've accumulated so far. So like I said, we were trying to do x plus 5 times x plus 5. When we did x times x, we get x squared, but that's the area of this square. Okay, so what I'm attempting to do here is show you how the area of this thing that I've drawn, this rectangle, which is actually a square, is related to this multiplication of polynomials. And when you multiplied this x by 5, that gave you maybe this rectangle up here. And you multiplied this x by 5, that gave you this rectangle over here, which is composed of 5 x's and 5 x's, which together give you 10 x's, which you're not surprised about because you know that. Okay? And then lastly, if we look up in this upper right-hand corner, we bring all these lines across, and we bring these lines up, you create another square. And that square is 5 by 5, or plus 25. And that's sort of a geometric way or an area way to look at multiplying polynomials. Why is this a perfect square trinomial? The question I'm asking is, why is this a perfect square trinomial? Because the area that it's represented by is a square. Okay? And other trinomials don't have that property, that aren't perfect squares at least. So the question is, suppose I start off a trinomial, something like this, and I say, hey, what would I love to have here so that it would become a perfect square trinomial? And maybe you look at that picture. If you look in this picture, you notice here was 5 and 5, and that had to be 25, right? And it turned out to be a 10x up here. Okay? Or maybe we'll just think about multiplying trinomials. So to get the number that goes here, we know it's going to be half of that, so 12 over 2, and then squared, which will give you 36. And 36 is the perfect number to go there. If you think about the area problem I was asking you to consider a moment ago, right, you'd have x squared in the corner here. You're going to have 6 units going up on this side and 6 units going up on that side. So then the question is, what is that? Well, that must have been an area of 36. Okay? So that's how you sort of figure out how you get the perfect number to add to this thing. All right. All right, so let's switch gears a little bit. Let's talk about graphing parabolas. Okay. And my claim is this, that every parabola you've ever graphed, ever, is really just this parabola, y equals x squared, but shifted left or shifted right, moved up or down. Maybe it's been turned upside down, reflected, and then maybe shrunk or stretched. So maybe it's made wider or maybe it's made narrower, so it climbs more quickly. But every parabola you ever look at is really just this one moved. Okay? So in order to sort of convince you of that, I want you to just do the following. Take a minute to think what that graph looks like, what this graph looks like. And then try these. And then finally try these, or this one. If you look at this parabola y equals x squared, it has the point 0, 0 on it. So the question I'm really asking is, what point on this graph is sort of the same, means the same thing, would have a y value of 0? When you answer that question, you say, what should you have to sub in to get back a y of 0? And sure enough, if you plug 2 in here, 2 minus 2 would be 0, square would be 0. So you sort of know that the vertex now, that new low point, is at 2, 0. Okay? But it should climb and grow the same as the other graph does. Okay. Let's talk about how this parabola y equals x squared just grows for a minute, and then we'll see how precise we can make these other graphs. All right, so if you imagine we go over 1, and think about that. If you went over to 1, 1 squared would be 1. So this is the point 1, 1. But if you went over 1 again in the x direction, then you'd end up going up how much? Well, if you give it a little bit of thought here, this is 1, 4 is the point, because x is 2. So you increase by 3 now. So our first increase is by 1. Our second increase is by 3. All right, so here's something sort of fun to realize. Let's go to x equals 3. 3 squared is 9, so it's way up here on the graph somewhere. And if we ask ourselves how much we increase by to get to there, to go from 1, 4, sorry, not 1, 4, but this was 2, 4, and this is 3, 9. If I want to get from 2, 4 to 3, 9, I have to go up by 5. Okay, so this confirms that it's concave up. Our slopes are getting bigger as x gets bigger. But then also notice the pattern in the increases. The patterns look like odd numbers. And sure enough, they are. Right? Pretty neat. So sort of a fun thing to think about is like, why does this always turn out to be an odd number? And it turns out you can show that pretty easily using some algebra. All right. So if we think about it, what I'm asking is this. We have x and y. We plugged in numbers like 1, 2, and 3. we were using the function y equals x squared, so we got back things like 1, 4, and 9. And we noticed that we had jumps that were odd numbers. There's also 0, 0 on there, which gave me a jump of 1. So if you think about it, what I'm really doing is I'm saying I've got a number, and I'm comparing it to the number that comes afterwards. That's what I'm doing. And I'm saying, if I take a value of x and I sub it in, and then I also plug in x plus 1 and sub that in, I'm expecting a difference that's an odd number. Well, at least that's what seems to happen, because so far we checked it out. We saw differences of 1, 3, and 5. So let's see, does this continue to happen? All right, well, we know that this would just be x squared, and we know that that would be x plus 1 squared. Oh, look at that. There's a perfect square trinomial hiding right there. Okay, if we square this out, we get x squared plus 2x plus 1. Okay, so let's think about that. We went from x squared to x squared plus 2x plus 1. That means we increased by 2x plus 1. But now the question is, what do we know about 2x plus 1 if x is an integer? Now I'm going to be careful here. I'm going to say x is an integer, meaning that we're not going to plug any decimals in for x right now. We're just going to plug in an integer. If that's the case, what do you know about the quantity 2x plus 1? So we know this expression is odd because we're taking an integer, we're multiplying it by 2. Anything we multiply by 2 comes back as even. How do you know that? Because if you take a number multiplied by 2, it means it's divisible by 2. Only even numbers are divisible by 2, right? Without a remainder, that is. And then we add 1 to that, and we land on the odd integer that comes right after that even integer. So we should expect an odd difference every time. Okay, so that's sort of a fun thing. What does that tell us about the graph? It tells me that if I want to graph, for example, y equals x minus 2 squared, then we could just think to ourselves, okay, what number's really acting like 0 now? 2 is. 2 is the number that when you plug in, 2 minus 2 is 0, you get back a y of 0. But instead of just sort of sketching this parabola, we can be more precise now. We know we can go up 1 over 1 this way, or up 1 over 1 that way. So our parabola is starting to take form. When we go out here to x equals 4, that's like the original parabola going out to x equals 2. You can plug it in here and get a y value, or you can say, all right, look, the parabola does the following. It goes up 1 over 1, back 1, up 1. But we know the next point would be over 1, up 3, over 1, up 5. So we can be pretty precise about what the rest of this parabola looks like. Okay? So this is just an expectation from now on. And you can also use some symmetry. You might as well draw this nice line of symmetry up here, and then you can reflect points. So this point comes over to here, that point comes over to there, and then you get the other half of the parabola. My picture's not perfect, but you get the idea. So a fair question might be, what about a graph like this? Y equals, and there's a couple ways it could happen. Suppose I gave you this equation. Okay? Now if this happens, what's happening is that these were my old y values. And now what I'm saying is I'm going to double all of them because I'm multiplying them all by 2. So in effect what happens is this. We go over to 2. We know this is our new 0 point. But here's what changes. Normally the parabola would go over 1, up 1. But instead now it's going to go over 1, up 2. All my differences are getting multiplied by 2 now. My next y value is going to be over 1, and instead of up 3, like previously, it's going to be up 6. So now we can see the graph is climbing much more quickly. And then I would advise you to use that symmetry. You end up with that graph. So sometimes, maybe in the past, you had a teacher tell you, oh, or you figured out for yourself, that if we multiply by 2, it makes the graph skinnier, people would say, more narrow. What's really happening is the y values are climbing more quickly. So it gives a perception of the parabola more narrow, but that's what's really happening. They can try and trick you. y equals 2x minus 2 squared, like that. Okay? So be careful with something like this, because it's not written in the other form. You can't just say all the y values have been doubled. As a matter of fact, here's what happens. You could be clever with algebra, and this really helps. Watch. I'm going to factor a 2 out from the inside. And then what do we know? We know that when we're squaring a product, for example, if I tell you to do 3 times 5 squared, you can do 15 squared if you want and get 225. Or you can take this 2 and square both of the things inside first. You can do 9 times 25, which is also 225. So if I use that same reasoning here, this becomes 2 squared times x minus 1 squared, or really y equals 4 times x minus 1 squared. So maybe when you first looked at it, you thought it was right 2, but it's not. It's only right 1. And the y values, instead of all being doubled, are actually all being multiplied by 4. So this graph is going to climb 4 times as fast as the previous one. So lastly, as promised, what does completing the square have to do with this? Well, I go back to my original claim. I said to you that every parabola that you've graphed is really just that original parabola, y equals x squared, moved left or right, up or down, flipped maybe, or made narrow, made wider. Okay? So here, I'm going to show you how we do that. Suppose I gave you this parabola, y equals x squared plus 6x plus 11. Now, unfortunately, when you try and factor that, right, nothing really happens. I can't think of any numbers that multiply to 11 and add to 6. So we're out of luck there. It'd be nice if it was a perfect square, wouldn't it? Wouldn't that be great? I'd love for this to be a perfect square, because then I can factor it and make it look familiar. Here's what I mean by that. Suppose I had said graph y equals x squared plus 6x plus 9. Well, now you can do a pretty good job with that. You just say, hey, that's y equals x plus 3 squared. Well, that means I just go left 3, put the vertex, go up 1 over 1, up 1 over 1, up 1 over 3, up 1 over 3, and get a perfect graph. Okay, that's what I would love to have. I don't have it. And here's where this might be new to you. But you always have the option to, you can write this in other ways, as long as it's equal to the original expression. So I'm going to write it like this. Okay, just a little bit of creativity, not much. Just a little bit of creativity. And the question I ask you is why? Okay, so the advantage is that we can factor this first trinomial. So it turns out to be x plus 3 quantity squared plus 2. I know exactly what that graph looks like. That graph is left 3, so 1, 2, 3, up 2, and there's my vertex. And from there, I go up 1 over 1, up 1, back 1, up 3 over 1, up 3, back 1, and I get a really good sketch of that parabola. Just one subtlety to be careful of. This completing the square trick that we know of only works if your leading coefficient is 1. If it's something else, we're kind of in trouble. So consider this problem for a second. 2x squared plus 12x plus 10. Okay, actually make it plus 11 again. I don't want to have a common factor there. Okay, and the question is, can we graph this without a calculator? So since completing the square does not work with a coefficient of 2, we're going to factor 2 out from the first 2 terms. And notice how I didn't bother with the last term at all. Okay, so I would love a 9 to be here. When I put plus 9 here, what I've really done is add 18 to this equation. So I need to subtract 18 out here. Y equals 2 times x plus 3 quantity squared minus 7. And once it's in that form, I know how to graph it.